can you see my screen? I think I tried to share it.
Yes.
Okay. The whole point of this workshop is it's supposed to be interactive. So as far as I'm concerned, you can chime in at any time, unmute yourself. I can't see the chat comments right now because I have sharing my screen. So feel free to chime in at any time. We're here to assist you in learning our systems. You'll be writing your own scripts with our help, and you'll be taking observations yourself. So I'm just going to go over a general overview of the GBT. Actually, Karen already gave some of this stuff, but I'll give a basic overview of the GBT. I'll cover some of the GBT science areas. I'll go over some of the performance and its capabilities, and as well as go into a little bit outline some observing strategies, because we're observing tonight. So not only do you get to be exposed the initial software tools you'll need to use to observe tonight, you have to write scripts. You have to think what sources we're going to observe, what you want your group wants to observe, and you actually have to carry out the observations tonight. So you're going to have maybe too much information overload. So, oops, let's see here. Okay, my mouse button actually moves the slides. Karen already showed this, but we have been around for a long time on site. We're the original site of NRAO. Although it was completed in 2000, I actually think the telescope really began in 2009, 2010, and that's when it finally was improved such that you could observe at high frequency on the telescope. Before that, you really couldn't do the highest frequency observations efficiently with the telescope. There are 4 key capabilities of the telescope, and not the ones I actually list here. The ones, one of them is it's a big light bucket. It's 100 meter. So you have a big light bucket, and it's unblocked. I consider that 2 separate key capabilities. The unblocked gives you unrivaled sensitivity in terms of low side lobes. If you're doing sensitive H1 observations, nobody can touches them, in the world on those kind of observations. We are in the radio quiet zone, and that's number 3. And then the 4th key capability from my point of view is our active surface, our actuators, which enables us to observe up to the high frequency, the 116 gigahertz. I mean, in principle, we could go higher, but you have an oxygen window there, and then so you'd have to go on the other side of that. And the efficiency does drop off once you get up at 120, 130 gigahertz. So here's just a diagram just showing the national radio quiet zone. GBT's over here, Sugar Grove's over here. You can Google that or Wikipedia that if you want to know something about that site. And it encompasses a huge area. That doesn't mean there's no cell phone coverage in that area. It just means if people put up towers and stuff, you see it goes all the way to Charlottesville. They can't just stick them up at an infinite height. So the goal is to keep the radio signals from cell phone towers and alike from getting into our valley where our telescope is. And then we also have another zone here, a 10-mile zone around West Virginia. So in principle, we could enforce that a little more than we do. But the people on site, they don't use microwaves, you don't have Wi-Fi. And the goal is to keep the telescope in the best radio quiet possible zone as possible. I mentioned the active surface. Here's just a picture of the actuators. It's too bad you guys aren't here. We take you up on a telescope. You get to see this up close and personal. But this is just a picture on the edge of the dish. The dish is this way going that way. And this is just one edge. And you can see in one corner, and you can see these are these mechanical actuators that actually move the dish around as the dish deforms due to gravity. You can correct for that, maintain a nice parabola. And our accuracy relative to our size is actually quite good. It's like a couple parts in a million, which is actually quite spectacular. So you have a 100-meter exposed dish with metal dish exposed to the elements, and you can maintain that to 200 microns roughly, or 0.2 millimeters over a 100-meter dish. It's really good performance. We already said this in terms of the unblocked aperture. So here just shows a picture on how you look at it. So the focus is over here, so the light is not blocked by those speed loops. there by the normal support structures that you see in traditional radio telescopes. Here, the Bond telescope at the left and the GBT at the right. And Karen already showed this, but just showed the relative imaging quality. This is to the same sensitivity level, just with basic calibration of the data. And you can see the dynamic range, having an unblocked aperture, is just vastly superior than that you would get when you have a blocked aperture. Pictures. Here's a picture of our subreflector. Even the subreflector, I mean, it's pretty big because we have a big dish. So the light hits the primaries down below and hits the subreflector and then goes into what we call a receiver cap in here. So it bounces here to down here, and their L-band here is in focus. If we did the tour, you would be walking up here and walking around here and taking pictures from the, well, with film cameras, of course, because you can't use digital cameras, from up here of the entire valley. And if you look at this is on top of the receiver room where you can, and then here's part of your view. So we have 8 receiver holes, these little, where you can put, this is in Gregorian focus. So we could put 8 different instruments in Gregorian focus, and then you have 1 prime focus feed. And this is a picture inside the room. And just to show, it does move all the way down to 5 degrees elevation and 360 degrees around and azimuth. So it can cover 85% of the celestial sphere. In terms of the science, we'll give you a listing. Here's just my listing. I think they overlapped. I didn't look and see if you're saying the same things. But roughly, one could argue we do about 30% pulsar science, 30% neutral hydrogen H1 observations, and then another 30% sort of chemistry, whether it be studying the nearby chemistries. And we do some high redshift CO as well. So that's roughly the breakup in terms of the relative categories here. So we do a lot of different things. Being a single dish, and people can bring their own, you can build your own instruments and put them on the telescope. It's very flexible. It's a flexible platform in that regard. You can keep upgrading the instruments and you have the collecting area. And our collecting area is big. I mean, it's the size of the collecting area of ALMA, basically, all within a single dish. So this is just going to be quick show and tell of some of the science that you can do with radar. We're currently, as Karen mentioned, we're looking to expand into transmission. Right now, we're just used as a receive station, but you can have Arecibo transmitting or Goldstone transmitting and us receiving, and you can observe nearby rocks or small asteroids. You pick pictures of the moon. It's nice. This is the one to the right is a radio image of the moon, and the one to the left is an optical image of the moon. You actually look down under the surface layers that you can't see optically with the in the radio, and you can see features that you can't see optically. In terms of pulsars, we say this, and I believe it's the case. The GBT is the premier pulsar observatory. It's part of the Nanograph project. I'm sure Ryan and company, well, people here, I'm not sure how many of you are pulsar people. If we were in the room, I would ask, but usually we have at least 30% or half the people that come here for these training workshops are working with groups that do studies in pulsar. So the Nanograph, what?
It's almost half, Dave.
Is it? Thank you, Will. So that's pretty standard. So, and Ryan will be showing you how to observe with pulsar. So we'll break up into spectral line groups and pulsar groups. Now the Nanograph project's trying to measure the background gravitational wave signatures of merging black holes. We should update this slide, and I apologize. Ryan, I should ask for a new slide for you because we have these, this was from 2010 where the data was in 2010, and we have dotted lines of where we would be in 2015 and 2015. And I think the predictions have changed too as we've gotten more sensitive. but we have detected gravitational waves with LIGO, and those are at higher frequency. So the lower frequency stuff, you could actually detect using pulsars as timer to measure the variation of those timing signatures to actually detect background gravitational waves. So that's one of the main projects. That's their driving project. But when you're observing pulsars, you can do a lot of other things. You can constrain the equation of state of actually dense matter objects. These different models here. You wouldn't really expect in the old days to get pulsars being more than like maybe 1 to 1.4 solar masses, not 2 solar masses. So that's saying something about that dense matter. You constrain fundamental physics, constraining gravity, testing the equivalence principle. You can do a lot of things with pulsar timing experiments. H1, like as we mentioned, unblocked aperture, I mean, it really gives you unparalleled sensitivity to detect extended stuff. Can people see my cursor? Will, can you see my cursor?
Yep.
Or not? Okay, good. So like these little blobs. So typically if you use an interferometer and you looked at a galaxy, you'd see the bright central parts of the galaxies, the compact clumps of the galaxy. You don't see this surrounding low surface brightness stuff. So with the single dish observations, you get a more complete picture of where all the faint gas is. So you can see gas in groups of galaxies, high velocity systems, clouds falling in or being pushed out, and clouds, tidal debris potentially connected between galaxies, and streamers. Here's a Magellantic stream. You can observe, this is just a result, it's a little outdated, but it's still a cool little result by measuring all the galaxies in the local universe, and you can you get the kinematics, and you can actually get a sense on the local large scale structure of the universe. We do a lot of star formation, and with the ammonia, I'll show you some ammonia. This is a GBT with the GBT with the KFPA. That's K-band focal plane array, which is 7-element pixel, where you can. So we have 7 pixels on the sky. And you can map basically large regions of the sky pretty quickly. We use ammonia because it is a dense gas tracer, and it's also nice to measuring the temperature. But anyway, you can use ammonia and other tracers to study dense gas from which stars form. You can look at a lot of star formation and a lot of structures now. With the Herschel mission, it showed a lot of interesting structures and filamentary structures. So, but Herschel was a continuum, primarily a continuum experiment. Well, these are spire observations. So you don't have anything with the kinematics of the gas. So when you observe with spectral lines of the GBT, you basically can get the gas kinematics. And from that, you can find regions. This is an example here from a paper where the gas is in falling. It's subthermal velocity dispersion, low velocity dispersion, and basically what's going on there, that large scale structure of the gas is falling in on a young protostar. This particular protostar has some outflows in it too. But anyway, with the kinematics of studying dense gas tracers, you can disentangle what's going on inside these regions from which stars are forming. Just a pretty picture. I always just like this picture from Rachel of the Orion molecular cloud, a GBT ammonia image in red here. This is quite beautiful. Anyway, the GBT is also used in VLB observations, very long baseline array, or VLBI, as a very long baseline interferometry. So you combine the data from the GBT with other dishes around the world, and you have very high resolution imaging observations. This is an example result where they measured using direct parallax observations of the Pleiades, which is used as a standard distance ladder metric. Masers, we've done a lot of maser work. The GBT is used to discover the masers, and then they follow them up for high resolution studies with the VLBA to measure the masses of the central black holes. You can also measure the Hubble constant directly. So that was an ongoing project. Another VLB result for the at 3 millimeters that's used in our we call it our 4 millimeter receiver up at 86 gigahertz, and using the GBT in combination with other 3 millimeter VLBA to measure the jet of M87. This is actually the same source that they have the image of the black hole at 1 millimeter. So it looks different at 1 millimeters than 3 millimeters. At 3 millimeters, you're seeing the jet, where the 1 millimeter higher resolution data and higher frequency data they got in, and you could see the shadowing effectively of that famous black hole image that came out, I guess it's 2 years ago. We do some high redshift CO. The Herschel mission went up there, they found a bunch of sources on the sky that were very red, but we didn't know their redshifts. And the nice thing about the GBT, we had an instrument that just could get the CO1 to 0 line. So you could just blindly look at objects on the sky, not knowing how far away they were, and use the GBT to measure how far they were away, get the redshifts from the CO1 to 0 line. This is actually looking at 2 objects at the same time to do an on-off observations. And we detected CO in both objects in the same data set at 2 different redshifts. And this one here is the first one that was done. And here's a beautiful picture of ALMA. These are lensed objects. So the object is lenses. So that's high redshift CO. There's a little bit of cluster. Well, actually not a little bit, quite a bit of the work done by Mustang. Mustang is a continuum receiver that works at 3 millimeters. It's a bolometer array. So I don't know everybody's background. Radio astronomy, a lot of times all traditional radio astronomy, you take advantage of the wave-like nature of light to measure the phase information. By having that phase information, you can actually down convert it to a different frequency and deal with the electronics. The bolometer arrays are more traditional astronomy in a sense that it's treating it as a photon. The light comes in, it heats up basically your element, and it's basically a thermometer array, but call them bolometers, and it's measuring heat. The nice thing about that, you can pack a bunch of those in and make a large format array. So Mustang 2 is basically 230 elements on the sky, and it's very sensitive for mapping regions. So they use it to do the SC effect, the Dovich effect. But anyway, you're basically see a deficit from the cosmic microwave background, from foreground clusters show us, and from that you can study these cluster structures. Originally they were going to study all the cosmology parameters, but that assumed all the clusters were spherical. Clusters have a lot of stuff going on it. So I'd argue it actually looks like it's better at studying cluster structures and formation than it is doing necessarily cosmological measurements, but it produced very high, it's a very unique instrument for doing high redshift cluster studies. Chemistry. I mean, the main goal, one could argue with a lot of chemistry that's being done, is trying to connect the chemistry in space with how life getting the fundamental blocks to allow life to form on Earth. And this is, again, a little bit outdated. I should update it. But there's 20 plus new molecules that have been discovered by the GBT. And they're not just simple, 2-atom molecules now. A lot of these are quite complex molecules. So, capabilities and performance of the GBT. Okay, and this is important as you plan your projects, basically. So we have, and sorry, this will be these will be in the sense of showing tables. You're never supposed to show tables, but I'm lazy. We're going to show a whole bunch of tables. These are mostly from our proposal guide, and it acts as documentation. If anybody downloads this presentation in the future, they'll get this documentation as well. Currently, on the telescope, you can only use what we have on the telescope. We do not have, Mustang 2 is not on the telescope. Argus is going up on Thursday, unfortunately, after you guys are gone. The W band's not on the telescope, Q band's not on the telescope, or either is Ka. So the highest frequency that we can actually use on the telescope, Mustang's on the telescope, but it's not cold yet and it's not ready to use, is the KFPA. So that's the highest frequency that's going to be available to us. So we have the KFPA, X band, C band, S band, L band, and I don't even know. I assume 800 megahertz is up, but I'm not 100% sure. It's usually 800 megahertz. Ryan, do you know? Is it 800 megahertz?
Yes, 800 megahertz is currently up.
So we have 800, L, S, C, X, and KFPA. That's what we have available to us. This just in terms of their frequency ranges and their different bandwidths. Obviously, if you go to higher frequency, you have smaller beams on the sky. Up and go all the way to Argus, which we don't have. We can get down to six arc-second beams if you go all the way to the highest end of the frequency range. The back ends are so that we call it back ends and front ends. The front ends are the receivers. The back end is the digital aspect of that. It's the recording of the data. We have Vegas now that can do both spectral line and pulsar observations. When you do your pointing and focus, you'll use the DCR. We do have another backend for the Caltech Continuum backend that works really well for, but it only works for the KA. And then we have specialized backends for VLB recorder and also a radar backend. So what we'll use, depending if you're doing spectral line work, you use the Vegas spectral line modes. If you're doing pulsar work, you use the Vegas pulsar modes, and then you'll be using the DCR for continuum and pointing observations. And if you want to do a continuum experiment, we can use the DCR for continuum mapping as well. Okay, this is also all the Vegas modes. I'm not going to go through them. We just a bunch of modes. Some of them more. There's a little overlap in some of its capabilities, but we do have 16 separate spectrometers. They're broken up into 8 dual polarization channels, 8 banks like A, B, C, D, E, F, G, H. If I did my alphabet right. And the V for Vegas stands for versatile, so you can combine, depending if you have, especially for the higher frequency receivers, you have multiple beams. You could break up the banks for any divide for different beams versus different spectral lines. We also have the capability to do subbanding, so for each bank you could actually break it up into 8 separate small chunks. So if you have a single beam receiver, in principle you can have up to 64 spectral windows across your band. 8 banks times 8 subband. This is the Vegas pulsar mode. They're set up for coherent and incoherent mode. Ryan and company will go over that for the pulsar groups. Our specs, I'm not going to go over that, our location, and that's just from our documentation. But I do want to note the fact that when you do, we're not going to go at really high frequency because we can only go up to like 26 gigahertz. But the atmosphere is important if you're observing above 10 gigahertz. It adds significantly to your system temperature, and it also attenuates the signal. So you get hit twice, basically. So it increases your noise and it blocks the photons from coming in. And it's important when you're observing a higher frequency, your conditions can change fairly rapidly. But the site itself is actually pretty good. Even though it's in the east, actually it looks pretty good. It's really good now. It looks like it's clearing up. I'm looking out my window. We'll have pretty decent, after this front goes through, pretty good weather coming up here in terms of low opacity. And in the winter season, we actually have around 50% of the time is actually acceptable in terms of opacity levels for 3 millimeter observations on the sky, which is pretty good for where we're located. We're not too high, we're only at 2,700 feet, but that helps. Also, high frequency, you get hit by the winds. With a 100-meter dish, it's like a 100-meter metal sail. So when you have high winds, the dish moves around a bit. And your ability to track a position on the sky, that air goes up with the square of the wind velocity. So basically, if you're up doing, we don't have to worry about too much. We're not going up to 100 gigahertz. So there's a big jump between, doing 10, 20 gigahertz up to 100 gigahertz. Because at 100 gigahertz, you really can only handle like 1 to a few miles per hour before you actually start to have the wind affecting your ability to track, where at 10 gigahertz, the wind could be going 10 to 20 miles per hour. And we do have low winds at night a lot, but ideally, so for the best 3-millimeter observations, you want to have very calm winds and very dry conditions and low opacity. And how do you do that? How can you schedule? People that have projects on the telescope know that we have this dynamic scheduling system, and this will be talked about more tomorrow. And the goal of this is you have a system that predicts, based on weather predictions, what the weather's going to be. So then we try to optimize the schedule. So you observe high frequency. The blue means good, the red means bad in this plot. So you wouldn't want to observe high frequency here because you're in the red, but you would observe high frequency in these days where it's blue. So by making these predictions, you can take advantage of the good weather conditions. So we don't do fixed schedules where we say, you get 3 nights on the telescope, observer A gets, whatever, October 10th, 11th, 12th. It doesn't work like that for that project. What we do is we have a computer, the system, you enable your projects, and then the system will pick which projects to schedule based on the weather conditions. And this is the only way we can take advantage of our high frequency. If we didn't do this, we would not be able to, micro schedule the high frequency projects so they can get the best weather. Right now, I guess this is a fair statement. There are roughly about 450 hours per semester that are available for high frequency observations. When I say high frequency, excuse me, I'm talking K-band, so 20 gigahertz all the way up to 115 gigahertz. So that factors in the opacity effect, which is about half the time, and half the time it's windy or not windy. And then we also have only a subfraction of the time as open skies time, funded by the NSF. This is just a plot just showing the T-sys. You have the oxygen line coming in here. We do have a gap in coverage, so we don't have frequency coverage. The water line. And our aperture efficiency, basically at low frequency, it's basically a perfect telescope in a sense of that the feeds are designed to only have a 71% efficiency. And by maintaining the active surface, the goal is to keep this as high as possible over here. If we have a bad surface, this would stay up high, but this would go way down here. And that's how it used to be. And the improvements, the biggest improvements were made in 2009 when they finally got the telescope working well enough that they could observe and see that some actuators were not set right. So these were broken. So they worked on all the actuators. This is an effective picture of the dish, basically, projection. So they went from a noisy dish to a clean dish, and this is the effective beam of a point source. Went from a big point source to a more compact point source as it improved the dish. And this plot here shows it sort of the history over time of the effective aperture efficiency. This was measured at 43 gigahertz, but you can extrapolate the measurements of 43 gigahertz to say what it would be at 80 gigahertz. And this shows the efficiency at 83 gigahertz over the lifetime of our telescope. In 2003, you see, you really couldn't use the telescope it had an aperture efficiency of under 10%. a few percent basically, unless you're at the optimal rigging angle of the telescope, where it's peak here at 50 degrees elevation. So and then in 2009A, they improved things a little bit, but this is the big jump but when they fix the actuators. But even when they fix the actuators, you could basically optimize the telescope for one elevation, but then it wouldn't work very well if you went to a different elevation. So if you're low elevation, this is still pretty low aperture efficiency at 10%. So we improved the model of what we call the gravity Zernicke model. That was more improved. It was pretty good in 2010, but we updated it based on the 2014 data and really flattened our response as a function of elevation. So, so this is the aperture efficiency. If you invert that around using the Ruse equation, this would be the effective surface errors, basically. So back in the early days of the telescope, we had a 0.5 millimeter, 500 micron errors with the dish, and then we pushed that down, trying to get down to 200 microns, 0.2 millimeters, about 0.23 millimeters right now. That's discussed in a GBT memo if you want more data. As we already mentioned, we can observe up to 116 gigahertz. Here's our second light. We did this, I didn't do this first, I did it second, where 12 CO from Orion. And that's on a log scale. This was shown, it shows that we can reach the theoretical beam even at 110 gigahertz. There's a beam size as measured as a function of frequency, the higher end of the band. There are calibration results for the, and anyway, the telescope's performing sort of as one would expect theoretically, and we've been measuring that and confirming that. And these are all in a calibration memo that was published last year as a GBT memo. So we won't go through all these details. This is all within that memo, but it does show that our telescope, the aperture efficiency at 80, this is at 86 gigahertz, it's about 35%. That's looking at a point source, basically. You get aperture efficiency. That means 35% of the signal you're effectively getting. The main beam, within the main beam, you're getting 44%. So if a point source is within the main beam, your main beam efficiency is 44%. As you look at larger and larger objects, the amount of your efficiency goes up because you're starting to pick up more the beam pattern. If you look at Jupiter, which is 43 arc seconds at the time that these observations were taken, and then you get 53%. Moon, you get up to over 80%. And if you do in the forward direction on the sky, it's 98.5%. That means 1.5% of the antenna pattern is seen, basically the ground. Now, if you take the forward direction and how much you see, this is called the forward spillover efficiency. It's 96.5 degrees. You multiply these two numbers together, that gives you a total amount of power inside sort of the beam and air pattern of the telescope, roughly 1 degree on the sky. So when you point to a position on a sky, 95% of what you see is within 1 degree of the position you're pointing at, which is really good for a radio telescope. You don't get that with unblocked apertures. It's more like the best you do is like 80%. One of the issues we have with such a big dish is it's pointing. We have a good pointing model. And what this plot shows here is the offset pointing as a function of distance on a sky. So if you look at two different points on the sky, they're separated by a set distance, how far off would you be if you pointed, let's say, 40 degrees away from your target source versus 10 degrees away from your target source. So the point of this plot is it's better to point nearby your target position, obviously, than to point very far away when you're doing high frequency observations. At 100 gigahertz, your beam's 7, 8 arc seconds. A 4 arc second offset pointing error would be quite significant in comparison to the beam. At L-band, it doesn't really matter, because there are beams like 9 arc minutes on the sky. You can point once, or like the pulsar people don't even point at all, a lot of them. It doesn't matter, because if you have our pointing error is 4 arc seconds, who really cares when you have a 9 arc minute beam? And the model works, we're still working on the model. It really works good for gravitational distortions, but we can improve, I think we can improve this model, our pointing results. If we do a little more work on studying our track as well as the daytime thermals, we're not doing a very good job during the day right now. And if you do Argus observations and W-band observation, I would argue it's better to use. The problem with Argus and W-band, there are not very many bright sources on the sky, so you have to point on something bright. So then this question is, would you go 30 degrees away to get a bright Argus source to point on, or do you go nearby? And then you have to switch receivers. And based on these offset pointing results, it's better to actually use your lower frequency receiver and point nearby your science target than far away with Argus, for example, where you might have to go 30 degrees away. So you could get with the better than 1 arc second offset pointing errors if you used a different receiver. So you can point with X-band and use those pointing results, because those are pointing results for the telescope for your Argus observations. This is sort of a summary. This is a recent PTCS, that's Performance Telescope Control System. I think that's what our acronym is. Sorry for the jargon. Project note number 78. In there we give a summary of the current GBT performance. Blind pointing on the sky, it's 10 arc seconds. That means if you just say, let's go look at just, but don't do any pointing at all, just look anywhere on the sky, you're going to be on average roughly 10 arc seconds away, which again, for L-band, doesn't matter, that's good enough. If you point somewhere on the sky, and then you go somewhere completely different on the sky, you're gonna be within 4 arc seconds, which is quite good actually. And if you point nearby your science target, you'll be of order 1 arc second away. And once you're there, we think we might be, and you're trying to track a position, we tracked it better than about 0.5 arc seconds. This still needs measurements. We improved the servo system a few years ago. We still haven't done the detailed measurements to confirm the tracking error. It could be as good as 0.2 arc seconds, and it's certainly better than 0.7. So that's why I put the 0.5 there, but it's somewhere between 0.2, probably 0.2, 0.3, probably about 0.3. In terms of our surface errors, without our active surface corrections, it's about 0.5 millimeter. With no OOF corrections, but with active surface during the day, it's 35 or 350 microns, 0.35 millimeters. I guess I should use 1 unit. And then at nighttime, without any OOF corrections, about 300 microns, but then with what we call our OOF corrections, which is out of focus holography corrections, which corrects for some thermal distortions. These are the corrections that we hope lastly long-term will assist in optimizing. With those kind of corrections, get down to 0.23 millimeters or 230 microns. And our long-term goal is to push that down to 200 microns, which might not seems like we're almost there, but just going from 230 microns to 200 microns makes a big difference at the higher frequency in terms of your aperture efficiency. So observing strategies. It's a very flexible platform, GBT. We have a lot of different observing options, and as Will mentioned, you can write Python scripts, you can do all kinds of crazy things as long as you're not putting the telescope in danger. And we have lots of instruments, and there's many different observing modes. Ron, who retired, if you go through all the patterns, I forget, there's like 10,000, there's basically many thousands of possible options in which you can configure to carry out an observation. So it's not like the VLA or ALMA where you have set cases in which this is how you're going to do your observations. There are only like, maybe 10 or so different types of modes that you could actually use. Here we have hundreds and hundreds of possibilities, which is great. It allows you to do anything you want. But it also complicates your ability to do the data reduction and have an automated pipeline to produce, science-ready data products for users. We don't have that here. So this is definitely more of a hands-on facility, and in some senses that's great, because for training purposes you can learn how to set things up for the telescope, observe with the telescope, and then you have to figure out how to reduce your data. And so basically some of this is pretty simple logic. You pick your receiver based on your frequency range. Obviously, if you want to observe H1, you can't use the X-band receiver because H1 is in the L-band receiver. So your receiver you choose, your instrument you choose, is based on the frequency, and then the back end you pick is based on type, observing type, doing spectral line or continuum or pulsar observations. And then you have different observing techniques, and that's based on what you're trying to do in terms of science. Are you doing point source science? Are you mapping a large field on the sky? Are you looking at narrow spectral lines or broad spectral lines? All those different decisions are basically, your observing techniques are based on the specifics on what you're trying to do. And also your calibration strategy also depend on your receiver and your science goals. So we'll go through this logic. This is a very streamlined logic, or a flow, a decision diagram, so to speak. So you have different observing modes. When we do radio astronomy, we do on minus off observations, because if your signal is much weaker, then you don't see it on an absolute nature on the sky. You have to typically difference it with respect to a reference signal, and by doing the on minus off, then you can actually see your astronomical signal. So there's different ways to do that off. One way we call frequency switching, which you're actually switching the LO frequency, so the bandpass signal. I guess I didn't want to show, we have all kinds of extra slides to show this graphically. Maybe we should for these training workshops. But anyway, your noise within your passband stays the same. You switch the frequency, and you can actually see the signal, and all the instrumental passband effects get canceled out. And that's called frequency switching, changing frequency. A more classic way to do it is position switching, where you actually can move the telescope to on minus the off. Now we have the multi-beam receivers. You can actually move your on between two different beams. We call that a nod. You move the antenna position, put the source in beam 1, and then you put the source in beam 2. That's like dual beam position switching, or we call that nod. Nod is actually the observing command you'll use within your Python script. And then we have SubBeamNod. Instead of moving the antenna, you can move the subreflector to put the source in the two different beams, and we call that SubBeamNod. So picking between frequency and position switching, this is for spectral line work. I don't have examples here for pulsar stuff. I'll let Ryan cover that. But for frequency and position switching for spectral line work, if you're doing narrow lines in a non-crowded spectrum, you can do frequency switching. If you're in a crowded spectrum, even though your lines are narrow, meaning you can have lots of RFI or lots of different, like if you're doing a chemistry survey and you have a lot of faint lines under there, you would want to pick position switching, because you wouldn't want to fold in signals at other frequencies onto your target frequencies. It makes it a little confusing. If you're doing broad line work, you should do position switching. And roughly the definition between narrow and broad line, it's fuzzy, it's not hard and fast. We usually do frequency switching for less than 10 kilometers a second, and broad lines for over 100 kilometers a second. So broad line you do for extragalactic work. The narrow line, is for galactic work. Observing mode, if you had a small source, meaning the source is smaller than your beam, you want to do line observations. And for position switching, and then you have to pick, there's different modes you can pick. So we have, if you have a multi-beam receiver, with 2 or more beams, you can do nod, and that's nodding between your two, using the antenna to nod between the 2 beams for position switching. And for Ka, Q, and Argus, you can actually use SubBeamNod if you have a point source. And we recommend for K band and W band to use nod, and that's because the two beams there are widely separated. And the SubBeamNod works for small movements of the subreflector, but not for large movements of the subreflector. So that's why it works for Ka, Q, and Argus, but not for K band and W band. If you just have one beam, let's say L band, you can just do an observation called on-off. And I have this nod, SubBeamNod, on-off are the actual commands that you use for the GBT. You can also do just track. If you want to observe a source in the sky, the command for the GBT is just track. And then you can put in offsets. Now, if you're doing frequency switching, all you need to do, you're not moving the antenna or the subreflector, you just observe with the track command and do frequency switching. If the source is, if you're trying to do continuum observation, and the source is small, you can do a daisy map. Daisy map there is just looping around. Whoops, I don't have a picture of it. It's just looping around in a daisy pattern like the petals of a flower. So every time you come towards the middle, you come over the central part of the map, and then you map the outer regions as lobes as you go around, as you cover the phase around the source. Anyway, this is a good way to deal with the 1/f noise for continuum observations, meaning you can cover your source many times in a short period of time. If you're doing a large map, a large source, and you want to map, and your map that you're targeting is much bigger than the field of view of the instrument, then you use the commands RA long map or DEC lap map. I told you we'd have too much information load, and this is a lot of information, but you can pull up this materials within the observing guide, but it's also, you can pull it up in terms of documentation when you're setting up your scripts, which you'll be doing this afternoon. If you want to map something that's smaller than your field of view of the instrument, then it gets a little more complicated. The optimal method, one could argue, depends on several factors. You could actually do so you could still do a short RA long map, but then you have a lot of overhead. If you're making really tiny maps with the GBT, it's a 100-meter, 17 million pound instrument. You have to turn that around. So you don't want to have to turn that around quickly. It's hard. You can't turn it around quickly. So there's a lot of overhead if you try to make small maps with the GBT. The daisy maps work if you're only interested like in the central regions, or like if you're doing a clump or a core. There are other modes that we call box scans, where you can find a box and randomly, not randomly, but you observe like a ping pong ball or a billiard ball bouncing off a pool table, sort of smooth turnarounds within the box instead of doing hard turnarounds back and forth. And then if you're trying to go really deep, you can do the old fashioned way where you just point and stare, and then you move the telescope. That's called a point map. You can make a grid map. In terms of antenna optimization, at the highest frequencies, you should be pointing and focus every 30 minutes to an hour. I have my general rules here. This takes like 5 minutes. So like at W band, it's basically during the day, you'd want to point every 20, 30 minutes. So you're spending 5 minutes pointing every 20, 30 minutes to try to keep the beam to get the pointing accuracy sufficient to carry out your science. Since we're observing at night and we'll be doing K-band at the highest, you can get by with pointing every 2 hours. And our sessions are only 2 hours, 1.5 and 2 hours. So in principle, you only need to point once. We won't be doing auto oof. We have no instrument on there now that doesn't auto oof, but we will be going, I guess, over that tomorrow. There's a lot of overhead with the auto oofs. The auto oofs are used to correct the surface, and you need that for Q band and W band. The oof solutions that you derive from the auto oof are good for 2 to 6 hours, but there's a 30-minute overhead associated with that. So people generally do it just once per session at night. And that's where we hope LASSI will come into play down the road to help make this more efficient, tracking our deformations of the dish over at night, which doesn't change as much, but potentially during the day. Like right now, we can't really observe during the day at high frequency and maintain a good surface. The daytime surface changes on less than an hour timescale, changes as fast as you can take the oof. You could take oof after oof after oof, and the solutions, you could just watch them change. So, and typically, if you do an oof during the day, you can actually do more harm than good because the surface changes more after an hour. So we don't actually do auto oof during the day. It's better if you observe during the day. Just use our default Zernike gravity model, not try to chase the thermals by measuring the oofs, because by the time you measure the oofs, the surface is always changed. And in fact, the surface is changing during the measurement, so it's not a good measurement. And that's all I had in terms of formal slides. Let's see if I get out of here. So I'll leave them up for a second. And oops, let's see here. I don't see, you see my screen. I don't, whoops. Chat. I'm going to open up the chat windows.
I could read chat.
So we have,
like, oh, you see it?
Yeah, yeah, I have it. Yeah, I pulled it up. Somehow I think I closed off, well, never mind. I'll stop the sharing, but I closed off the little Zoom window. It's buried somewhere. So we have a question here. So is KU band receiver available or not? It is available in general, but it is not available now. So no, it is not available now. Can we get the slides from the different presentations? Yeah, we'll make those available to us. So let's see here. And then we have a question earlier on. What is the observing capability of the GBT of the sun? You can observe the sun. Does the GBT have solar attenuators to observe the sun? Well, we do in a way. It's called our paint. We paint the telescope with the white reflective paint with basically, you can think of it, bits and pieces of sand in it. So it scatters the infrared light, but focuses the radio light. Now, I've done this with other facilities, and I know we could just look right at the sun. And typically we try to avoid the sun. And maybe if Tony's online, he could, I'm not sure what the rules are of direct sun. I don't think.
Yeah, I'm here. We can look straight at the sun.
For all our receivers, or just
keeps the temperature increase at focus down to only 1 or 2 Kelvin, so it's quite manageable.
Okay, I hadn't done that. Thank you, Tony. I've done a
distant temperature.
We did that at the Owens Valley antennas. They actually have these high polished mirrors, and they installed them in backwards by mistake. But then we noticed, oh, by putting them backwards, they scattered all the infrared light, and that allowed us to look at the sun. So they left them in backwards. But anyway, so then it can be used for the VLA. Yes, that's right. So yeah, you could use the GBT with the VLA to look at the sun. That was that question. Let's see, are there any other questions? Oops. Oh, thanks, Tony, for putting it in the chat window. And then another question, do you have a simulator where we could practice many of the GBT capabilities for observations? Not exactly, but sort of. And what I mean by that, if you used our sensitivity calculator, the sensitivity calculator, when you pick your receiver, you pick your different modes off to the left within that calculator. As you make more choices, it blocks out things that aren't possible. So the sensitivity calculator can be used to pick, figure out how many spectral windows can you put on for a specific receiver. And then we have, in terms of looking on the sky, we have this tool called Clio, and we'll go over these tools after this talk and upcoming talks, where you could pull up maybe not this function. The Clio scheduler will show you on the sky how to look at things like what the current sky is for a particular time. So in that sense, you can see when your source comes up, and it also gives you, it even has built in there, you can click on different points and see how long it would take to move from one part of the sky to the other part of the sky, which helps in terms of planning observations if you're doing a lot of different sources. So that's not a true simulator, but we have some tools that assist in terms of the planning of your observations. The mapping calculator too, you can put in the different sizes of the maps, and then it'll give you an actual observing block that you can the Python code that you could use to carry out the observations.
One more tool in that vein is in Astrid, whenever you're writing your scripts, there's a script validator that will tell you whether the script will work or not.
Yeah, that's a very good point. That's the first thing. You don't want to, yeah, it's good at finding your commas and your parentheses in the wrong place type of stuff. Okay. What are we doing on time? We're doing okay, aren't we? Will?
Yep, we have a few more minutes before Larry leads everyone through Astrid, speaking of scripts.
Okay. And we will just maybe give people a few minutes break or whatever, right? Until that starts. If we get ahead of schedule, we won't start the talks early, right? We're going to maintain to the schedule.
Yeah, we could have a 2-minute break or so. There is one more question.
Yeah, okay. Will the recordings of the talks be available? Do you want to talk to these points, Will?
Yep. So we will plan to put all of the talks and PDFs of the presentations on the same website. So this will be on the remote observing website. I'll put a link in the chat here. The PDFs can be available pretty soon. The talks will take probably about a week for us to get them trimmed down and uploaded. But yep, they will all be online.
Cool. Oh, well, yeah, Tapazi said, yes, a 5-minute break would be great. We have to be careful when we do it all remotely. We can't, no coffee breaks here or anything like that. So we have a virtual coffee break. Any
final questions for Dave? The rest of the talks today are about accessing the GBT system through remote tools and then Astrid and Clio, like Dave mentioned.
So did you send out everybody's accounts? I guess people have accounts that have a homework assignment to do here. On it and stuff.
I've sent probably about half of them out.
Okay, so they're still coming.
Yep.
And the goal would be to have everybody to log in by, our talks finish by lunchtime, is that right? So we want to.
No, there's one more session before nominally lunch, depending on your time zone.
Yeah.
And then 2 more talks afterwards.
Okay. But anyway, everybody needs to log on and test out their account by the afternoon session.
All right, hearing no other questions, if one comes to you, just put it in the chat, but we'll take a couple minutes and restart at 10:30 with Larry Morgan.
Thanks, Will.
Yep, thank you, Dave.